Have you ever pondered if time marches forward uniformly for everyone, or if its pace could change depending on your journey through the universe? It is a fascinating question that opens the door to some of the most profound discoveries in physics. The answer, surprisingly, is that time is not absolute. The physics that explains the light clock phenomenon is Albert Einstein's special theory of relativity. Specifically, it is the concept of time dilation, which states that time can pass at different rates for different observers depending on their relative motion. The light clock provides a beautiful and intuitive way to visualize this effect. At the heart of special relativity are two fundamental postulates. First, the principle of relativity states that the laws of physics are the same for all observers in uniform motion, meaning motion at a constant velocity. Second, and crucially for the light clock, the speed of light in a vacuum is the same for all observers, regardless of their motion relative to the light source. Imagine a light clock as a device with two mirrors, one at the top and one at the bottom, and a photon of light bouncing back and forth between them. Each bounce represents one tick of the clock. Now, consider this clock moving past you at a very high speed. For an observer stationary with the clock, the light simply travels straight up and down between the mirrors. However, for you, an outside observer watching the moving clock, the light has to travel a longer diagonal path to hit the mirrors because the mirrors themselves are moving horizontally. Since the speed of light must be constant for both you and the observer on the clock, and the light in the moving clock travels a greater distance, it must take more time to complete each bounce. This means the moving clock ticks slower than a stationary clock, a direct demonstration of time dilation. This phenomenon has significant practical implications, even beyond theoretical physics. For instance, the Global Positioning System, or GPS, relies on precise timing signals from satellites orbiting Earth. These satellites are moving at high speeds relative to us on the ground, and their clocks experience time dilation. Without accounting for these relativistic effects, GPS devices would accumulate errors of many meters per day, rendering them useless for accurate navigation. The factor by which time is dilated is often called the Lorentz factor, represented by the Greek letter gamma. This factor depends on the object's speed relative to the speed of light. As an object approaches the speed of light, this factor increases dramatically, meaning time dilation becomes more pronounced. It is not just clocks that slow down, but all physical and biological processes. So, the light clock is not just a clever thought experiment. It beautifully illustrates how special relativity fundamentally alters our understanding of time, demonstrating that time is not a universal, unyielding constant. Instead, it is a flexible dimension intimately intertwined with motion, always ensuring that the speed of light remains the ultimate cosmic speed limit for everyone, everywhere.